So this is a tutorial of Raja, and these slides were made by the entire Raja team, and I'm Robert. I'm part of the Raja team. I work part-time on Raja, and my other time is actually spent porting like Fortran code to the GPU. So that actually works. You can ask me about that after this talk, I suppose. So let's see. I'll try to describe how Raja enables your performance portability today, and I'll give you a little bit of background on how you might want to think about porting your application to Raja and to parallel paradigms in general. So the longer version of this talk has a bunch of exercises that you can do in your terminal, but because I only have about 2 hours, I opted to have mini quizzes inside this talk. So yeah, if you thought you came here to have fun, then yeah. No, they shouldn't be too bad, okay. And then hopefully by the end of this, you'll have some idea of how to incorporate Raja piece by piece into your codes. Okay, so please don't hesitate to interrupt me and ask questions at any time. If you have further questions beyond this week or after this talk, you're also welcome to email the Raja Dev mailing list. We're very responsive. All right. Raja is a header library of C++ abstractions, right? And our goal is to help you write portable code that's single source. So your one source code with Raja, can run on the CPU or the GPU, and you shouldn't have to tweak things too crazily to do that, right? In doing so, we're trying to insulate your application from like the hardware specifics of programming on GPUs and whatnot. And so to do that, Raja provides all sorts of parallelization techniques and performance tuning options. So I'll go over loops and complex loops that you can do in Raja, reductions. I'll go quickly over scans and sorts and a bunch of other things. And Raja enables more specific performance tuning options in loop tiling, thread local data, and GPU shared memory, which I won't go over in detail, but I'll have a few slides on those. So again, the goal of Raja is so that you can have a single source code that can run on both the GPU and the CPU, and this should be hopefully easier for you to use, right? Raja was designed to be easy to understand, and so that you can very carefully and very incrementally put small pieces of Raja into your code at a time and build up and port your code slowly over time, right? This is to not force a major disruption to any of your existing code, and Raja does this by cleanly encapsulating all of its algorithms and parallel for constructs. And yeah, we try to make it easy to parameterize your execution types with type aliases, and we enable you to do systematic performance tuning. Okay, and these are all the things that our code teams at Lawrence Livermore, they find that are good about Raja when they use Raja. The Raja project has been going on for, well, about 8 years now, and we're steadily increasing in the number of users that we have and the number of contributors. We have a lot of issues open, but we also have a lot of pull requests to address those issues and other things. Raja is actually a piece of the Raja portability suite. So the Raja portability suite has these 4 different repos in it. Raja itself is one. Umpire over here allows you to manage your GPU memory and other memory. And then if you want automatic data movement between the CPU and the GPU, you can use Chai with that as well. And then all of these sit on top of CAMP. CAMP is just a library of metaprogramming tools that all three of these codes use. So you can actually use Raja by itself, or you can use Raja and Umpire, or you can use Raja, Umpire, and Chai altogether. And we feel that this kind of setup allows you to very incrementally port your code to using these constructs, right? Because you can start by porting your loops to Raja. Then if you find that you need more advanced memory management techniques, you can use Umpire. You can start throwing in Umpire with that. And then if you want even more memory abstractions, then you can throw Chai on top of that as well. Okay. We have a number of links on our GitHub webpage. And you'll find the user guide there that will have actually most of this material and more. We have this Raja project template repo, which is just a very small example of how to use Raja. Most people who are getting started with Raja tend to take a look at this. And this tells you basically how to build Raja with all these other components as well. Okay. And then the proxy apps repo is just some of our Lawrence Livermore applications are put into this repo, and they use Raja, and this is a way for us to have our code teams to have a little bit of exposure to the outside world. And then finally, there's the Raja Performance Suite, which is a set of benchmarks which help us look at how the compiler is working with Raja, and it benchmarks the performance of Raja. Okay. Let's see. So today I'm just going to go over most of the Raja features listed here. I'll talk about simple loops, reductions, iteration spaces, data layouts, and views, and then also more complex loop kernels. And then I'll go over some other more advanced features of Raja briefly, and also each of the components of the Raja portability suite, just for completeness. And throughout this talk, I'll talk about things you should think about when you're using Raja, and general things to think about when you're thinking about parallel algorithms. So let's start with really simple loop execution. This kind of code might seem very familiar to you. It's just a C code for the DAXP operation, right? Double AX plus Y, and we write a loop over this to do it for vectors, right? If we want to Rajify this, we can start off by trying to do this, right? This is a Raja for all. This is like the parallel for idiom that you guys are probably very familiar with. We replaced the for loop with this for all that has these things, an execution policy, an iteration space, and then a lambda. Okay, so there are a couple more things that need to go on top of this, or before this. We have to, the execution policy is a type alias for which backend to run this loop on. And the iteration space is defined by this typed range segment from 0 to n minus 1. It's not inclusive of the end. Okay. So you'll notice that we changed the for loop part of this, but the loop body is still the same, right? We don't want to change that part of the code because that's usually where the important stuff is. That's part of the single sourceness of Raja that we're trying to achieve. Now, this for all has basically 4 types of things going on in it right now. It's got the execution template, which is this for all templated function, and the execution policy type up here, which tells us where to run the for all, the iteration space, which is the range, and then the body, which is the C++ that we want to run. The for all over an execution policy can be run on basically any substrate that we provide. So we have CUDA GPUs. You can run it on the CPU with OpenMP. You can even run OpenMP target, which is OpenMP on the GPU. We have HIP. We have a SYCL backend. That's all I can think of right now. And the iteration space that you provide to the for all is basically the indexing that you want to have happen over this, okay? And then, of course, that iteration space translates to the int I over here, and you use the integer I that you pass into the lambda to iterate properly over your loop. Okay. So the loop body, yeah, the loop body is a C++ lambda expression, as you've seen, and my colleagues before me have talked about lambdas to quite some detail, but yeah, the last point of this is that you have this lambda, but you still need to think about thread safety in this context. What happens in the for all is that the for all is if you want to pass in a CUDA policy to this, it will try to run on the GPU, but it will run iteration space number of threads at the same time. So on the CPU, that doesn't hurt you too much, but on the GPU, that is, you have to be careful about synchronization. Okay. These are some of the execution policies that we provide. Loop exec is actually the same thing as your standard for loop here. So if you want to just have a normal C++ for loop, you just use loop exec. Oops. OMP parallel for is the OpenMP policy. It puts a pragma OpenMP parallel for on top of your loop. For CUDA execution, we have the CUDA exec, but you have to pass in the block size, which is the number of threads per block, and so on and so forth. This is the OpenMP target, and this is even, we even have, yeah, Intel thread building blocks as well. Okay, and this is a more complete set. Some of the execution policies that I didn't go over are sequential, which is it puts a pragma no vector on top of your for loop so that you force yourself not to be vectorized and you force yourself to run sequentially. We have a backend for HIP GPUs or AMD GPUs. And yeah, we have one for SYCL. We have a SIMD execution policy which attempts to force vectorization if the compiler thinks it can. And then this is not really a for all policy. We have tensor and matrix core. I would call it an API that you can try to use. That's kind of experimental. Okay. Questions about this so far? Okay. Yeah. So hopefully from what you've gathered from this is that applying a Raja for all is not too hard. Your loop body should hopefully stay the same in most cases. But the for loop syntax is a little bit different. You put a for all instead of a for loop, right? Before I go too much further, I should talk about other considerations as you're trying to use Raja. So as you probably saw, Raja kind of uses a lot of C++ templates, right? This piece of code here is actually an implementation of the for all loop internally in Raja. And you can see that it takes in 3 template parameters: the execution policy, the index type, and then the loop body, right? And these kind of have to be known at compile time, or they do have to be known at compile time. But if you notice in my examples that I've shown, I only pass in the execution policy. For example, this is the sequential execution policy. And that's because the other two, the index type and the loop body type, are inferred by the compiler when you build the code. Okay. And you do pass them in as arguments into the for all function. So, right. And the lambda part of all this is, it's a closure that is a function that stores a data environment for you. It's kind of like a functor, but kind of easier to use. Under the hood, lambdas are functors. They're just instantiated at the call site, right? Maybe you've seen this before, but a C++ lambda has these three things, right? It has the function body, which should look pretty familiar, as a parameter list, which is like any parameter list for a function. The unique thing that it has is this capture list, which attempts to suck in all of the variables that you need for the lambda in the enclosing scope. Okay. In Raja, we attempt to always capture by value here with the equal sign. That's because if we want to run on the GPU, if we try to capture by reference, the GPU will try to look for CPU addresses, and then it'll be very unhappy. Right? Okay, right. So the parameter list is the parameter list. It mirrors what's going on in the segment here, the range segment, or the iteration space. Right? It tells us which variables to iterate over in the for all, from 0 to n-1. And finally, if we want to run this sort of for all on the GPU, we have to mark the lambda with the device annotation here, so that the compiler knows that this is for the GPU. In Raja, we have macros for this, so you can use those macros. We also have a host device macro as well, so that you can tell the compiler that, hey, this for all can be run on both the CPU and the GPU, and then it will compile that way. Kind of unlike Cocos, Raja doesn't provide a memory model. It does not provide any notion of memory management. We have another repo called Umpire, which does that if you want. And it is up to you as the programmer, when you're using our for alls, to make sure that all the data that you want is actually accessible on the GPU if you have something like a CUDA exec policy here. Okay, so yeah, they must be accessible on the GPU A and B, because we're using a device policy. We've even marked this lambda for device usage, right? And the way that you normally do this is you can just manually manage your memory for the GPU. You can use CUDA malloc, and you have to CUDA memcopy from host to device and back. You could use unified memory, or you can use other tools in the Raja portability suite like Umpire and Chai. Okay. I mentioned that the longer version of this tutorial has a bunch of exercises that you can do. Those exercises are all in our GitHub repo. So if you go to Raja and you go to exercises, you can see all of those. And all of those exercises actually use unified memory. We just use CUDA malloc managed. So you can, if you're trying to port your application with Raja and you're just starting out, you can just kind of do what we do in our exercises and start that way. Okay, any questions about all this so far?
Yeah. So if you don't use the unified memory management system, the purpose of course device, if you don't have unified memory management, the purpose of cross compiling on different hardware devices will not work.
You can just use the CUDA malloc. If you don't have unified memory, you should have just normal CUDA memory, right? Device memory. Did I answer your question? Maybe I didn't quite hear it properly.
Yeah, we can talk about it.
Okay. Other questions or concerns? Okay. So here's the first quiz. So this example is actually in the Raja repo under exercises vector addition. And basically, I have this C-style loop that's under OpenMP, right? And I am wondering what you guys think should be the correct execution policy that should go into the for all here. Anyone have any ideas? Yeah, this one's pretty easy. It should be OMP parallel for exec, right? That one's not too hard. I made that one a little bit too simple. How about this one? Just a normal for loop. Okay, I hear sequential exec, I hear loop exec, yes. Loop exec is the right one because loop exec basically allows you to write, it translates to normal C-style code and it lets the compiler do whatever optimizations it can. It'll allow it to vectorize if it's possible. Sequential exec is the one that forces no vectorization and forces it to run in order. Okay. And this one isn't really a question. This should be pretty obvious. If you want to use the CUDA execution policy, what it would translate to is something like this, where you have, a global function that should go onto the device, and then you do the triple chevron call of that. Right. Okay. And notice that in the CUDA execution policy, we have to pass it a block size. The block size is number of threads per block. Okay. Any questions about how the for all works before I go on to reductions? Oh, I'm sorry.
For the block size, do you have a wave-tail Raja that I want Raja to deduce it for me?
Let me think. We used to have a default block size, I believe, but now we make you pass it in. Yeah. Yeah. Other questions about this? Okay. Or if you want a default block size, you can, write an alias with a block size, and then you just put that alias into this.
The issue is that you might want to decide the block size based on querying from the CUDA runtime what is the good block size.
Okay. So there's a different thing for that. Under the hood, this will look at how long your n is here. And then it will look at your block size and it'll try to give you that number of blocks, basically. Yeah. And then you can even further optimize by passing in a second template parameter here called blocks per SM. Yeah. You probably know what that is.